Probability is something we work with almost every day. You want to know what is the probability that you're going to have rain or snow today, so you know whether to take an umbrella or wear a coat. You want to know the probability you're going to pass a class. You want to know the probability of winning the lottery. You want to know the probability of um, getting sick. All these things are things that we look at for different things in our lives. Definitions then are things that we need to kind of look at when we're talking about probability. And all those things I described are what are called random experiment. A random experiment is any activity or observation whose outcomes cannot be predicted. So, like, I can say what's the chances of it raining or snowing today, but I can't actually say for sure exactly what it is. So I can't actually say, hey, it will or won't. I can't actually say that. So a random experiment is kind of an experiment where you don't actually know which outcome will actually happen. You can kind of think about the outcomes, but you can't say exactly which one will happen. So a trial is a repetition of a random experiment. So if I flip a coin one time, it's one trial. If I flip a coin 6 times, it's 6 trials. What we like to deal with a lot is what we call our sample space, which is a set of all possible outcomes of that random experiment. So when I flip a coin, notice I can get either a head or a tail. So looking at that, my sample space would be listing head and tail. If I flip a coin twice, then I can get a head head, a head tail, a tail head, and a tail tail. Notice head, tail, and tail head are different because the ordering actually does matter. If I roll a die, you can get 1, 2, 3, 4, 5, or 6. Those are the things you can get. If I am drawing a card from a standard deck, my sample space would be a listing of every single card, all the way, all 52 of them. So I know it seems like a lot to list all 52, but it helps you to do probabilities if you list them. We will be looking at what we call events. Event is some kind of subset of that sample space. So in other words, I may only care about getting a heart. Then I would list all the ways to get a heart. I may, when I'm flipping a coin, only want to look at getting 2 heads. So I'd list those 2 heads. So, and then what we want to do is come up with what we call a probability space or probability distribution. And that's where an assignment of probabilities to each one of the outcomes in the sample space. So as an example, a head tail, if I have the sample space head and tail, then the probability of getting a head is 1/2. The probability of a tail is also 1/2. So this is my probability space would be the actual event. Actually, I guess we should call it outcome. And then the probability. And so you'd list your outcome, which would be head, and the probability is 1/2. And then you list your outcome of tail, and the probability again is 1/2. So what you have is, this is what is known as our probability space or probability distribution, where you're listing all the outcomes and their probabilities. So you could also look at if 1, 2, 3, 4, 5, 6, if you roll a die, then you have a probability of 1, probability of 2, all of them actually are the same. It's all 1/2, 1/6. If you want to look at the probability of getting an even, so if your probability space, if your outcome that you want is the even number, then there are 3 even numbers in here, so 3 out of 6. Probability of odd would be also 3 out of 6. Which you could reduce if you want to. I don't particularly like to. I like to know it's 3 out of 6. But if you want to, you can reduce that to 1/2 and then make it into percent if you want to. I prefer the fractions because I know there are 3 ways this can happen. Out of 6 ways anything can happen. Another example is if I have head, if I flip 2 coins, this again is my sample space. The probability of getting a head is 1/4, probability of a head tail is 1/4, and so forth. And then I can actually look at, let's say, instead of looking at each one, but I could say what's probably getting 0 tails. 0 tails means you get 2 heads. So there's 1 out of the 4 ways of that happening. If I want to look at 1 tail, there's 2 ways of getting 1 tail, tail head and head tail. So it's 2 out of 4, and 2 tails would be 2 t, which is 1/4. And again, you can make them into decimals or you can leave them as percentages. One thing to notice is in all of these examples, if I would add these up, I'll get 1 here. If I would add up the 3, 6, and 3, 6, I'd get 1. If I add up all the 1, 6 here, I'd get 1. If I add up these 1/4 plus 3/4 plus 1/4, I always get 1. So the probabilities the probabilities in a probability space must always add up to 1. There are 3 different ways of finding probabilities. One is what we call the theoretical probabilities, which is actually what we were just using in that last example. This is based on a mathematical model using equally likely outcomes. And what that means is you have to know that the outcomes are going to have the same chances of happening. So going back to our examples here of our event space, notice that the probability in 1, probability 2, 3, 4, 5, and 6 were all 1, 6. They all were equally likely to happen. That happens if you have a fair die. If you don't have a fair die, then that doesn't happen. Same thing here with your coin. You get a head tail. Notice they each have the same equally likeliness, 1/2 and 1/2. Again, assuming that you have a fair coin. So you do want to make sure you think about those things. So let's say we have 2 fair dice are tossed. What's the probability that the sum of the numbers is 6? And first you want to state your sample space. So you could get a 1 on the first die and a 1 on the second die. That's one outcome in our sample space. You can get a 1 on the first die and a 2 on the second die. A 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. Then I get a 2-1, a 2-2, a 2-3, 2-4, 2-5, and 2-6. And all the way, the same thing happening. Again, each one of these, going all the way down to 6-6, each one of these outcomes are equally likely. It's just as likely to get a 2-2 as it is to get a 1-6. So there are 36 here. I actually like to list the whole sample space out because it gives you some ability to look at some things here. And then we can look at the number of ways of getting a sum of 6. Now, one of the things is the probability of an event. If you have equally likely events, is the number of outcomes favorable to E? In other words, how many ways can E happen over the total number of outcomes? So this is why writing out your sample space, it means that all you're doing is counting. You're counting how many outcomes. There's 36. You're counting how many ways to get whatever the event is you want. So in this case, we want to find the probability of a sum of 6. So 6 means you either have a 5-1, you have a 4-2, you have a 3-3, you have a 2-4, or you have a 1-5. Notice it nicely makes a diagonal. So if you write out the whole sample space, you will see this whole diagonal. So if I were to go ahead and write in that this is a 2-5, and this one is a 2-6, notice that here 6-1, 5-2, 4-4, 3-4, 2-5, 1-6, those all add up to a sum of 7. So you can see that this diagonal tells you how many ways can you get a sum of 7. There are in fact 6, 1, 2, 3, 4, 5, 6. So that's why I like to write out the whole sample space. You can actually just use your diagonals to find these sums. And the probability of a sum of 6, because there are 5 ways that can happen. There's 5 out of 36, so it's 5 out of 36. Again, I prefer to leave it as 5 out of 36, but if you want to make it into a decimal percent, you're more than welcome. But what I like about this is I know there are 5 ways this can happen out of 36 ways. And that's theoretical. The next one is what we call empirical probabilities. This is where you actually do the experiment. So an example is if I have a coin and I don't know if that coin is fair, then I would actually have to toss that coin a bunch of times and see what probabilities I get. So in this experiment, let's say we toss a coin 20 times. If we get a 9, we get 9 tails. So we get a tail 9 of those 20 times. So we get 9, which is how many times we saw the event happen, over 20, which is how many times we actually did the experiment. And you get 9 out of 20, which is 0.45 if you want to make it into a decimal. And notice that 0.45 is close to 50%. So theoretically, we should get the tail 50% of the time. And that's pretty dang close. So that tells me, hey, this coin is probably a fair coin. It may not be, but it probably is because the experimental probability is close to the theoretical probability. The last one is what we call subjective probabilities. These are based on personal experience or intuition. So, in other words, you're just kind of saying what's the probability that's happening. If you haven't been into a car accident and ever or for a really long time, then you would think your probability of getting into a car accident is really, really low. However, if you just got into one, then you might actually think that that might be a little bit higher. So this really is subjective. It really is a personal experience. Everybody's answers will be different depending on your values and what your experience is. One other thing about probabilities we can use for all three of these. So theoretical, experimental, and subjective probabilities can talk about something called a complement. A complement is where two events are complements of each other if their probabilities add up to 1. So I like to think of it as one event is, let's say we have event E. The complement of E, which we write as E with a bar over top of it, is every way that E can't happen. So if you're looking at the complement of getting a sum of 2, or let's just go a little bit easier, of getting a 2 on one die, the complement would be getting everything else, a 1, a 3, a 4, a 5, and a 6. So the probability of an E of that event happening plus the probability of its complement is equal to 1. What's nice about this is that means if you want to know one of these and you know the other, all you do is subtract from 1. So 1 minus the probability of E equals the probability of its complement. So if you know the probability of you getting the flu is 20%, then the probability of you not getting the flu is 80%. And so you can kind of think of complements as being knots. Also is another way some people think of it. So let's find the probability of drawing a 7 from a standard deck. So the probability of a 7, there are 4 different ways of getting a 7 out of a standard deck. Again, if you need to, list out the sample space and then count how many 7s there are. There are 52 cards in a deck, so it's 4 out of 52. Again, if you want to reduce it, you can. I prefer the 4 out of 52 because it tells me there's 4 7s out of 52 cards. The complement of a 7 is not drawing a 7. So that means you get every other card. You can get a 2, a 3, a 4, a 5, a 6, an 8, a 9, a 10, a jack, a queen, a king, and an ace. So instead of listing all of those and counting them, we can use the idea of a complement. So the probability of 7 complement is 1 minus, kind of what I said up here, 1 minus 4 out of 52, which is 48 out of 52. Again, if you want to reduce it, go right ahead. What I like about not reduced also is that I know that 48 out of 52 is bigger than 4 out of 52. So I can actually then compare them and see that this one's more likely to happen than this one. We also have something called odds. Odds are not the same as probabilities, but they are in fact related. Unfortunately, in our daily lives, we hear a lot of people talk about odds and probabilities as if they're interrelated, as if they're the exact same, but they're not. They're actually related to each other, though. Given the probability of an event is, let's say, the probability of E, then the odds for the event are the probability of E over its probability of its complement. So you can kind of think of it as this is the number of ways that E can happen, and this is the number of ways that E can't happen. So that's kind of the way I like to think of it, as the number of outcomes in favor of E and the number of outcomes not in favor of E. If you like odds against, because some people like to do odds against, then it's going to be the complement over the event. So let's say 2 fair coins are rolled. Find the odds for and against rolling a sum of 6. So probability of a sum of 6 we found before was 5 out of 36. Therefore, the probability of not a sum of 6 would be 1 minus 5 out of 36, which is 31 out of 36. And so the odds for a sum of 6 would be 5 out of 36 divided by 31 out of 36, or 5 out of 36 divided by 31 out of 36 that way. Flip the second one, and you see it's 5 out of 31. So again, the way to think of it is 5 is the ways that E can happen, that sum of 6 can happen. 31 is the number of ways that 6 can't happen. So it's 5 to 31. So we don't usually write them as fractions because they're not really fractions. In a way, they sort of are, but they're not in terms of probability. So we can sometimes write them as 5:31 or 5 to 31. So that means that it's 5 ways to 31 ways it can't happen. You do not write these as decimals or percents, so you either write them in the fraction, which I don't like that much. I prefer the colon or the 2. The odds against a sum of 6 would be basically turn the sum upside down. So it'd be 31 over 5, or 31 to 5, or 31 to 5 that way.